Well, good afternoon, everybody, and welcome to the last of our webinars here, Webinar Day at Smart Vision Europe. We've run two webinars already looking at decision trees and correlations, and this is our third and last one of the day. We're looking at regression techniques in SPSS statistics. My name is Jarlath Quinn. I'm joined online today by my colleague Rachel Clinton. She'll be making sure everybody's logged in correctly. If you haven't joined any of these before, you should be aware that we do record the webinar, so you'll be able to listen to it again afterwards. There is some slideware here that I'll be using, and we'll email a link out to you after the session's ended so you can download those materials. If you think the session is particularly relevant for colleagues who are unable to join and you can get enough of them together, then it may be possible for us to arrange a rerun of it. The best thing to do is just send us an email or give us a call, and we'll see if we can do that. And with regard to asking questions, all the lines are muted, so please use the chat panel. Rachel will be fielding them, but if we run out of time, we will follow up with you afterwards. We do, as I've said many times before, we do tend to get questions emailed into us after the session's ended, so don't be afraid to do that once you've had time to digest what we're talking about. I'll try and remember to check the chat as near the end, but I can't guarantee it. It just depends on time. I usually manage to, so don't be afraid to ask a question either way. If you don't know who Smart Vision Europe are, we are a technology company, we're an analytics company, and we're a gold accredited partner to IBM, as well as partnering of a company called Predictive Solutions and Data Robot, and we specialize in advanced analytics and data science and big data technologies and statistics and AI and all that sort of stuff. Bear in mind, though, we do work with open source technologies such as R and Python. We're a relatively small organization, but we're made up of a team of individuals who have pretty deep, long-standing experience with statistics and statistical analysis and analytics within the software industry. I started working for SPSS in 1995, and prior to that, I'd been a researcher using statistical programs like SPSS. And over the years and over the decades, we've developed, of course, quite a lot of deep experience of applying these technologies and these techniques that we're going to be talking about across the commercial and not-for-profit sector in a range of different applications, whether it be in insurance or manufacturing or charities or housing or healthcare or gaming. Today's agenda is that we're going to be looking at regression. We're going to start off talking about giving you an overview of regression techniques and how we explore linear relationships using tools like SPSS. We're going to then introduce the concept of linear regression by performing a simple linear regression. That's where we regress one variable against another. And then we're going to expand that out to look at multiple linear regression to make predictions. And then we're going to compare and contrast that with a technique known as logistic regression, where instead of trying to predict a continuous value from a numeric variable like sales or age or something like that, into predicting the response probability with logistic regression, where we got a category variable like a yes/no outcome or a true/false outcome or something like that. And that's a very different type of regressive technique, or at least the output is different, and it's got some conceptual um, uh, idiosyncrasies associated with it, which we're hoping to hopefully cut through. Certainly, it is much easier to understand logistic regression once you've got your head around linear. So it's a good gateway to that type of technique and other forms of regression. So what do we mean by the term regression? Well, people use the term regression to refer to all sorts of different things. Within data science, regression is often used just to refer to techniques where you're trying to predict a number outcome as opposed to a category outcome. You're trying to predict a value. But in reality, regression refers to a family of statistical techniques used to predict outcomes and generate estimates for hundreds and thousands or hundreds of thousands of applications. Linear regression is used when the outcome is continuous or scale in nature. So it's a number, it's a value, it's the amount of something, it's revenue, or it's visitor numbers, or it's age or performance on a test or something like that. And it models the relationships between fields using effectively straight lines. So it doesn't use curvy linear relationships, it uses straight line relationships where a 1 unit increase in one field has the same effect on the other field. The 1 unit increase in one variable has the same effect on another variable all along the scale. That's what we mean by linear. Whereas quadratic is a variant of linear regression where the outcome is continuous, but the relationship is usually curvilinear in nature. We have a video that looks at this in more detail. It's freely available on our YouTube channel. And logistic as well. We have other videos on that if you wanted to take a deeper dive into that in today's session. But this is usually used when the outcome consists of two and sometimes two or more categories. If you're using multinomial logistic. And nonlinear regression, well, nonlinear regression is usually used in its strict sense when the target relates to something like growth or power law. So, for example, it's used in things like disease outbreaks. It would be used in things like the COVID epidemic, which is a very particular distribution. It's not linear. The growth of COVID outbreaks isn't linear. You know, as we've all seen those famous curves that relate to growth. It's also used with power laws, where as something the likelihood of an increase or the increase in a target doubles, let's say, every 24 hours or something like that. So it's a very particular case. We're focusing here on linear regression and later on logistic regression. And these are very much the foundation elements, I would say, of the regression family and the gateway to all of the other techniques that we're mentioning here. So where are regression techniques used? Well, I've personally worked on things like modeling the relationship between promotion spend and revenue. So the amount of money you spend on marketing, you know, if you double your marketing budget, how much does that affect the revenue that you increase? Could you predict how much revenue you're going to get if you increase your marketing budget by a certain amount? Estimating things like pollution levels following heavy rainfall, where we've been looking at monitoring pollution in estuaries and in river courses and in along shorelines, and using heavy rainfall in the previous days to estimate what the pollution level is going to be, because the two are correlated. Predicting tourism revenue based on exchange rates and air travel costs. You know, air travel has a big impact upon tourism revenue and tourism numbers in certain states, and changes in exchange rates can affect that as well. You could do analysis predicting student test scores using factors such as the student's previous test scores or how their peer group is performing within the same class. Estimating website hits based on retweets and follower numbers. So you could look at social media activity around a certain topic that relates to a particular website. Maybe it's a media website, the BBC or something like that. And can you actually predict the number of website hits and how much, say, a particular social media platform has an impact upon that? And even things like predicting sales of barbecues based upon temperature forecasts, because of course those things are related to one another as well. So regression is a term that's actually a shortened term. The full term is regression to the mean, meaning falling back towards, regressing towards an average value. It's a pretty old term. Regression as a technique is well over 100 years old. And as I say, regression to the mean is what it's really referring to. Here we have a very simple scatter plot of relationship between years of high school completed by father and year for a respondent, and the years of high school completed by mother for a set of respondents. And as we can see, there's a rough linear relationship. The more the respondents, the more years of education that the respondent's father had, the more years of education the respondent's mother tended to have as well, not surprisingly. You can actually run a little procedure in the SPSS charts, what's called jittering the points, where you can see where all the data is kind of clustering around here. So you can see this, certainly within this data set, a lot of people clustering around about 13 years of education here at this point, completed by father and by mother. And what we can do is we can use one field to predict another using regression. In fact, if we take the average of one field, we kind of just average it out, you can see that it starts to literally regress to an average. It regresses to a line, if you like, and that's at the heart of regression to the mean. So when we look at all the average number of years of high school completed by mother and what is the average number of years of high school completed by father, and so forth. So we can start to see a relationship forming here that's is obviously fairly linear in nature. Now that straight line that underpins that is known as the line of least squares. And indeed, when we do regression analysis, it's all about that averaged line that is created, that really simplifies, in very crude terms, the relationship between two or more factors and what the average is. And it's called the line of least squares because what the line is doing is it's trying to minimize the distance between each individual point and the line itself, the average itself. So the regression line is drawn so it minimizes the differences between the points in itself. The differences are literally referred to as the residuals. So, if you're 10 years below the line, then you got a residual of -10. And if you're 5 years above the line at a certain data point, you have a residual of 5. It just means the error or the residual. And this is called the line of least squares. The reason why it's called the line of least squares as opposed to least residuals, if you like, or least values, is because, of course, the minuses and positives, if you added them all up, they would cancel each other out. The -5s would cancel out the +5s, the -10s would cancel out the +10s. So, as is typical of statistics and mathematics, what they tend to do is they square the differences. So -5 becomes 25 and -10 becomes 100 and so forth, and they add those up. So it's just a convention, really, that they're squaring the residuals, they're squaring the differences, and that's where the term line of least squares comes from. The line being, as I say, this average relationship, the mean, the regression to the mean between the two factors. You got to be careful though. Using straight lines is kind of a very brutally simple way to represent relationships. It can be very effective, but it is kind of brutally simple. And those of you who were on the correlation webinar I did earlier on will have seen this chart already. It's called Anscombe's quartet, and it is used literally to show that you get the same relationship, you get the same line, even when the data is very different from one another. I mean, up here, it looks perfectly reasonable in this first quadrant up here between the variable y and the variable x. Looks pretty good fit there. If the relationship, however, is curvy linear, the line just ignores that and just says, well, I'm still going to take an average across that. So it warns you that, linear regression isn't always going to fit the data perfectly well, because the data might not be very linear in nature. The relationship between the two factors may not be very linear in nature. We need to bear in mind things like extreme values can affect the line. The line is a kind of average after all. It's a bit like calculating the average height of somebody, or average height of a classroom, and then somebody walks in who's 10 feet tall. It makes the average height go up if it's a small classroom. And even in this last situation here, where we only have really two values on the x-axis, we have the value 8 and the value 20 or 19 or something like that. It still attempts to and draws a line through that, basically bulldozes a line all the way through that every time. So the point is just be careful. Linear regression is just a straight line at the end of the day, trying to simplify the relationship between one or more factors, as we shall see. Okay, before we get to that, again, the people who've been on the correlation webinar earlier on, you'll seen me talk about this set of charts as well. This refers to correlation values, and they're kind of a gateway to linear regression. If you're teaching linear regression, you normally start off teaching correlations first of all. Correlations are a way to measure how strong the linear relationship is between two factors. And here we have a series of data points, where each data point refers to a vehicle, an automobile, a car. And we have measures like the horsepower of the individual cars and the vehicle weight. And we can see here there's a very, very strong relationship, strong linear relationship here. If we were to express that as a correlation, in this case, it comes out as 0.859. And now correlations run from +1 to -1. So this is quite close to +1. It's quite close to, I'm not going to say it's a perfect relationship. Obviously it isn't, but +1 would mean it is a perfect relationship and every single data point would fall perfectly along a straight line. But it's a pretty strong relationship, and it means that you could use horsepower to predict vehicle weight and vice versa. Here, the relationship is less straightforward. It's a bit more fuzzy, a bit more noisy, as we would say, a bit more random error in it. This is a relationship between miles per gallon and time to accelerate from 0 to 60, indicating simply that if your car takes a long time to accelerate from 0 to 60, it's probably got pretty good miles per gallon. That's probably a bit more fuel efficient. And that has a much weaker correlation value here, 0.4, closer to 0 than it is closer to 1, indicating that it's closer to a kind of random relationship. And here we have a negative relationship here between horsepower and time to accelerate. Whereas if your car takes longer to accelerate from 0 to 60, then the horsepower tends to be lower. And vice versa. If the horsepower tends to be lower, your car takes longer to accelerate from 0 to 60. And hence that's given a reasonably strong correlation here of minus 0.7. So it just means that as one value increases, the other value decreases. And you see these relationships all the time between things like, reflex reaction time and alcohol intake or something like that. As one increases, the other tends to go down. We need to bear in mind, of course, is that we'll often get relationships where there isn't really much of a relationship between the two factors. Here we have miles per gallon against mileage, which is just really the age of the car, and it looks like a random cluster of points. That correlation value is very weak. It's very close to 0. And as a result of that, we would probably say that there's no real linear relationship here between these two factors, and why should there be? And the last one here, again, a reasonably strong negative relationship, but notice that the straight line, even though this correlation is purely based on this straight line, it doesn't really fit the data very well. This is actually kind of a hook shaped, and we might transform the data. In this case, I've taken miles per gallon, I've squared it in order to create this chart. And for that reason, sometimes statisticians take the square root of a variable or the log of a variable in order to straighten out the relationship between one variable and another, because it's an easier thing to do than doing a more complex form or a more obscure form of linear regression, say a non-linear regression. Sometimes it's just easier to say, well, look, I'll straighten out the relationship. I'll take the log of the value. And you'll see that a lot. You see that in econometrics a lot, where they take the log of the GDP, for example, to try and predict some sort of regional economic output value. Okay, the key point here is it's something that people won't have seen on the correlations webinar, is that we can actually turn correlations from these obscure values that run between +1 and -1 with 0 in the middle indicating a random relationship. We can actually turn them into percentages. So if you have a correlation here of, say, 0.859 and you square that, you multiply it by itself, it comes out as 0.738. If you turn that into a percentage, it's 73.8%, and that's called the R square. So it's like a correlation value is the R, and the square of the correlation is the R square. And that shows us what percentage of the variation in one field can be explained by the other. So 73.8% of the variation in horsepower can be explained using vehicle weight, and vice versa. 73.8% of the variation in vehicle weight can be explained using horsepower. If you want to visualize this, imagine a Venn diagram of two circles representing the variation in horsepower and the variation in vehicle weight, respectively. If they overlap by 73%, that's kind of showing you how much variation one variable allows you to explain of another. And the reason we use that is because this is the key measure that is used in linear regression to tell us how well the model fits the data. It's literally called an R square, and in this case, actually, it's called an adjusted R square, which is a slight adjustment to it. But obviously, the higher that number, the more the data fits the predicted, or the model fits the predicted the actual values in the dependent or the target variable that we're trying to regress to. We're trying to predict using linear regression. So how can we express these linear relationships as models? How can we go from saying, all right, there's a 73.8% fit. This is a really good way to, using horsepower, I could really predict the weight of the vehicle. I could do a very good job of that. if I wanted to create a little model from that or create a little equation where I could feed in, say, the horsepower value, and it would give me what the vehicle weight was or what it estimated the vehicle weight was, or vice versa. Feed in the vehicle weight and it would estimate the horsepower. What would that equation look like? Well, the simple answer to that is to ask yourself how long it takes to cook a chicken, because that is a regression equation, normally speaking. And in fact, people have more than one rule of thumb for how long it takes to cook a chicken. If you ask people in a classroom, of course, how long it takes to cook a chicken, they'll usually say, well, it depends. And you'll say, well, what does it depend on? They'll say, well, it depends on the size of the chicken. And you'll say, what do you mean the size of the chicken? Do you get a tape measure? And they say, well, no, I mean the weight of the chicken. Okay, so weight of the chicken uh, is a factor that impacts how long it takes to cook. And it turns out that if you're using a cookbook, such as Delia Smith or Julia Child's cookbook, they have different little equations. So Julia Child's came up with 7 minutes per pound plus 45 minutes, which is very different from Delia Smith's equation of 20 minutes for every pound of the chicken plus 20 minutes for good measure. The point is that these are the equation for a straight line. And sometimes this equation is expressed in mathematics as y equals mx plus c, or sometimes in statistics as y equals a plus bx. It's the same equation. It's just different letters swapped around. It's exactly the same. The point is that we have what's called a coefficient. We have the actual value of the independent of the variable, the independent variable, which is the weight of the chicken, and we have this plus 20 minutes or plus 45 minutes, which is the constant, the bit you add on. So this Dealey would say 20 minutes for good measure. So it means that, if the chicken weighs, 1 pound, it would be 20 minutes plus 20 minutes, take 40 minutes to weigh. Assuming that this is all, of course, assuming that the oven's at a certain temperature, and the chicken is, hasn't just been taken out of the fridge, and hence, depending if you're using different temperatures and different settings, you may well find that you have a slightly different equation. But if we're just using weight, and we're assuming at 200 degrees Celsius or something like that, or 180 degrees Celsius, this is how long it would take to cook the chicken. And this is literally a linear regression equation. So it is really quite often effectively a simple rule of thumb. And what we do when we do analysis in SPSS using linear regression is we obtain this equation. It actually gives you the numbers, it gives you the constant, and it gives you the per pound. What this number is, the 7 minutes per pound, is the coefficient. Or the 20 minutes per pound, that's the coefficient for that equation, plus the two constants. And these values we can use to help us predict an outcome. Okay, so for example, if we return back to the example we looked at earlier on at years of high school completed by mother and years of high school completed by father, when you do a scatter plot of that in SPSS and you ask it to fit a line through it, the line of least squares, it will give you the R square, saying this 38% of the variation in one variable overlaps with the variation in the other variable. Tells you how accurate it is. And it also gives you the equation. So it says, look, you've got the constant here of 2.89 years, just under 3 years, plus 0.74 times x. So if you took 10 years of education for the mother and wanted to predict how many years of education it would be for the father, that would be 10 times 0.74, which would be 7.4 years, plus 2.89, which I don't know what that is. It's roughly just over 10 years. And, that equation is true all along this line here. So that is our 20 minutes per pound plus 20 minutes for good measure. That is our y equals mx plus c, or y equals ax plus b, or whatever equation, whatever way you want to express it, with a coefficient and a constant in every occasion. So this is a very simple linear regression that we're seeing here, and it's just giving us the equation automatically when we ask for it by adding a line to a scatter plot in SPSS. But of course, we have a linear regression procedure itself. So let's have a look at a linear regression in IBM SPSS statistics. We're going to skip out to SPSS statistics. Here we've got a data set, and it's a data set I use a lot. It's a really good one because it's so flexible and we can use it to illustrate lots of different things. Let's say I'm really interested in predicting people's current salary. I'll just move that to the end there. This current salary, it's in dollars. And I wanted to measure the relationship between, say, people's starting salary and the current salary. Can I use starting salary to predict that? Well, let's look at correlations first. Let's go to the correlation here. I vary it. And I go current salary against beginning salary, or other way around, because correlation doesn't have a direct direction. I click OK at that point. It tells me the Pearson correlation here is 0.88. Okay. So that's the correlation. That's not the R square. To get the R square, I'd need to square that. I'm not entirely sure what 0.88 squared is, but if it was 0.9, then it would be 0.81, wouldn't it? It would be 81%. And if it was 0.8, then it would be 0.64, it would be 64%. And if it was 0.7, it's 0.49 or 49%. It's interesting, actually, because if you look at correlation value, if you go correlation value of 0.3, that's 9% overlap. Correlation value of 0.4, 16%. Correlation value of 0.5, 25%. Now the two circles within our Venn diagram are just overlapping by a quarter. 0.6, 36%. You need to get to 0.7 before you're almost at the 50% mark where the circles are overlapping by half. And above 0.7, it means that you're explaining more variation in one variable than you're not explaining, because you're over the 50% hump, if you like. So it's not a linear relationship in the sense that you get the same step change or the same amount that's explained with each increase. As you increase the correlation value slightly, you actually start to explain a lot more of the data. So if I wanted to build a linear regression of this and express it as linear regression, I would go to Analyze and down to Regression this time and go to Linear. You can see that under regression, there's lots of different regression techniques I can have here. Linear is the classic way we would do this, linear regression. Our dependent or our target variable is people's current salary. And I'm going to use beginning salary as my independent. And I can just leave everything else as it is at this stage. I don't need to do anything else. It's just run with the default settings and see what that produces for us. And we click OK at that point. And when we click OK at that point, what we find is you usually find no matter what technique no matter what package you're using, whether it be, Stata or Minitab or R or SAS or anything, you generally get very, very similar output from one package to another. There's a sort of convention with the way in which regression output is shown. And it starts off here just telling us that we're entering one variable to predict this outcome, which is beginning salary. It's being entered. And it gives us a model summary here. It tells us what the R value is. Remember, the R value that we saw earlier on is the correlation value, 0.88. That's Pearson's R. There's the R value, 0.88. If you square that, it's not quite 0.81, but it's actually 0.775. So 77.5% of the variation in current salary can be predicted using beginning salary. Now, what is it conventional within statistics is that you actually quote the adjusted R, which really takes into consideration the number of cases that you have and the variation in the data. It's a slight adjustment. It's always less than the R square. So the adjusted R square takes it down slightly to 77.4%. So when people say, what's the fit of that model, you would normally tell them, well, the adjusted R square value is 0.774. And the next thing you get is what's called an ANOVA table. This is sometimes called an omnibus test. And an omnibus test here isn't really doing that much. It's simply telling us whether or not using beginning salary is effectively better than just using beginning salary to predict current salary is effectively better than just taking the average. And if that value is less than your alpha threshold here, in this case, it's less than certainly less than 0.05. It is regarded as statistically significant. In this case, it's less than 0.01. In fact, it's less than 0.001. So, and it's basically saying, yeah, you can say that this variable or this model you're producing is better than effectively a wild guess. So we don't get too excited when we see that the ANOVA table is statistically significant because, it only has to be it only has to slightly correlate with the dependent variable. This adjusted R-square value could be quite small, really. It could be down like 0.2 or something like that, and you'd still get a statistically significant relationship here. But it is a kind of convention, this omnibus test. I'm saying, yes, okay, this is better than a wild guess, better than simply taking the average. And therefore, you move on to the meat, if you like, the heart of the regression analysis itself, which is the coefficients table. And you remember, we have this equation that we talked about earlier on, which is y equals mx plus c, or y equals a plus bx. So what we're looking for here is what's the c, what's the a, what's the constant, what's the plus 45 minutes, what's the plus 20 minutes, and what is the per pound? 20 minutes, is it 7 minutes? What is it? That's the coefficient, and it gives us both of these values because it says the constant, the bit that doesn't change, is equal here to $1,928. The nice thing about this column here, B referring to the coefficients in the table, the elements of the table, is measured in the same units that the dependent variable is measured in. The dependent variable here is measured in dollars. So it basically says everybody kind of starts in this model with $1,928. And then if you want to predict somebody's current salary, well, the current salary is worth $1.9 or $1.90, $1.91 if we're rounding up, $1.91 for every unit of their beginning salary. So if their beginning salary was $10,000, we wanted to predict what the current salary was, it would effectively be $19,000 plus $1,928, just under $2,000. So it'd be just under $21,000 it would be coming at. That's what you'd be predicting what the current salary is. So it's really easy to interpret because they're in the same units, and it's one of the things that make linear regression, quite attractive to people because we can interpret these values directly. And now this value over here, we're going to come to in more detail in a moment. Just before I get to that, we've got these standard error values here. This is really a measure of reliability. We're not going to talk about this in too much detail. It's really beyond the level of this webinar, but suffice to say, that's used to help us assess whether or not each element, what's argument, if you like, in the equation that we're producing here, each element in it, the constant and the coefficient 1.9 here, whether or not they're statistically significant. And certainly this is just below 0.05, so it's just about statistically significant. This is a lot less than 0.01. It's actually less than 0.001, so that's definitely statistically significant. But we've got the standardized coefficient here. It says beta. What that should say is just B. Beta here means B. That's what it means. It means it's a standardized version of this, because these are in the original units. These are in the units of dollars. These are not. These are standardized values here. Now, if you look at this number here, you've seen this number before. It's 0.88. It's the same number up here in the R value. And it's the same number up here in the Pearson correlation. That is showing you what the partial correlation is of beginning salary against the current salary. Now, partial correlation is a way to measure how much unique variation, if you like, in rough terms, one variable adds or shares with the target variable. And it's unique at the moment because there's only one variable in there. It's not sharing this equation with any other variables. So the coefficient is exactly the same. It's basically the same as the correlation. As I add in other variables, though, this beginning salary variable here has to share the equation with whatever variable I add in there. So let's say, imagine we had, we're trying to predict how long it takes to cook a chicken. If we put in 20 minutes per pound plus 20 minutes for good measure, and somebody else comes along and says, I've got a more sophisticated model of that. It's actually it's actually 15 minutes per pound plus plus yeah, something like 1 minute for or 10 minutes for every 10 degrees Celsius plus 5 minutes for good measure on the end. The equation's been changed because you've added in an extra element, which is the temperature of the oven. And it has to share that space of it. And as a result of that, of course, we have to modify the fact that, you've got this additional variable in there. And so in the same sense, if I went back to analyze and down to regression here and went to regression again, so I went down to linear, and I added in another variable. Let's say we pick an education level in years. Look at that. Click that, add that in. Now we have a higher adjusted R square value. It's going to 0.79 here, as beforehand it was in the model summary 0.77. So it's now gone up a little bit, 0.79, it's a little bit more accurate. And now the constant is actually negative. It's actually saying take off $7,000. You're going to take that off nearly $8,000. And beginning salary is now no longer worth $1,900. Sorry, $1.9 or your current salary is worth $1.9 of every beginning salary. So we're now worth $1.67 of every beginning salary. And actually, for every year of education that you have, you get an extra $1,000. We can see these are all statistically significant. And then once we've done that, we take off $7,000 to kind of adjust it. So this is a negative constant at that point. Now, look what's happening over here. Standardized coefficients. You can see this value here is now dropped to 0.771 in the presence of the variable education level years. This no longer has a value of 0.88. It's dropped a bit because it shares some of the variation with education level. It's kind of stolen some of its variation. And education level is really quite weak here. It's only got a correlation here, 0.172. Well, we could see that the R square only went up by a small amount. Went up from what will it go up from what, 0.77, something like that? 0.774 to 0.792. It only went up a little bit. So it isn't adding a lot. Why is that? Well, it's because if we look at beginning salary and education level, they're correlated with each other. They're correlated with one another. So you tend to have, a higher beginning salary if you have more years of education. They're both kind of measuring the same underlying thing, if you like, which is, your value in the marketplace, if you like. So if I were to run the linear regression again and I threw out beginning salary and just put in education level in years, look at the beta value here now. It's 0.661. It's the same as the R square up here. When I add in the beginning salary again, it drops to 0.172 because it doesn't have as much unique variation to bring to the model. And this is an issue that people spend a lot of time concerning themselves about when you have two variables which are really highly correlated with each other. In the cooking a chicken example, for example, if you were trying to predict it based upon temperature and you added in like oven pressure, well, they're basically measuring the same thing. The pressure in the oven is related to the temperature. So if you're measuring the same thing and you're trying to put them both into the same equation, then you may find that the beta code values get so small that it really not doing much, and it's just adding. It's a bit of junk. It's adding to the equation, and you don't want that. Okay, so let's go back. Let's add in a few other variables in. Let's add in age. Let's add in months since hire. And let's add in previous experience in months. Notice that the method here I'm using is enter. That means I'm forcing them in. It's often called forced entry, irrespective of whether or not they help. And when I force them all in, you can see that the R value now has jumped to 0.81. So it's a little bit more now, 81% of the variation. Notice as we look down through here, one of these variables, previous experience in months, isn't even statistically significant. And age adds very little to it. In fact, age is saying for every year older you are, you actually earn $102 less. One of the reasons why that is the case is because some of the people with the lowest earnings in this data set are the oldest people, and that's because They tend to be working in the custodial group, like caretakers and facilities management. So they're not paid as well as the managers who tend to be younger. So age can actually be a negative factor here. You can see that previous experience. Well, if you're older, you have more previous experience. So these two things are correlated with each other. So that's saying that, you actually get $8 less for every month of previous experience you have. So that's how we're explaining this. We might say, okay, look, let's take previous experience out. Or alternatively, we could do this. We could actually ask it to build the model step by step. We could say, okay, look, build it forward. Forward, think of forward as a bit like building a house of cards where you start off with one layer and then you add another layer, another layer. Backward, however, is like Jenga. That's where you throw everything in and you tick out variables which aren't contributing to it, and you're hoping that you still end up with a quite stable equation at the end of it. Stepwise is one where they can go in or go out step by step. It tends to be frowned upon, so I tend not to use it. I'm going to use forward here. If I click OK. What that does is it builds 5 models. And each time you can see it's putting in a different variable each time. And you can see that the R-square value here is increasing 0.77, 0.79, 0.803, 0.809, 0.81. I mean, some statisticians would say, look, for this extra variable you've just added in here, it's actually, you're only getting, a tiny amount more variation explained, but you're adding in an extra term into the equation. Maybe you should stop round about here, 0.803, just stop with 3, because it's, you're not getting much for your extra variables. Here we have 5 ANOVA tables, and here we have 5 coefficients tables, and it's telling us which variables have been excluded each step. So the first step here is beginning salary goes in, what hasn't been added at this stage. Everything else hasn't been added at this stage. Next thing that goes in is previous experience of months, and that goes in second, leaving education level, age, and months entire, and then education level and age is excluded, and age is the last one to go in there. And we can see that we're getting this quite complicated looking coefficient table. If I double click on it, I can actually click on this little button here and call up the pivoting trays. Click on that. And that allows me to actually drill down into each bit of it. So I can say, look, oh, hang on, I've done the wrong thing. I put the wrong, didn't want that. Didn't want to put the variables in there. I wanted to put the models in there. That's each step in. So it allows me to then say, okay, here's model 1. Look, beginning salary goes in. We've seen this before. Here's model 2. Look, previous experience is going in. It's actually negative, but it's statistically significant. Model 3, it's now added in months since higher. Then model 4, it's added in education level. Come in. And then on the 5th step, it's added in age. Interesting, look what's happened. Previous experience, which was previously statistically significant, is now no longer significant. That's because age is stealing its thunder somewhat, because previous experience and age are so strongly correlated with one another. So you might have to think about that. You might want to rerun the analysis, not use that variable, or not use age, or use a ratio of one to the other. These are problems that people have to deal with when they're building equations and linear regression. We generally tend not to want to put models, factors in which don't help predict the outcome. Now, if I wanted to save these predictions, so actually see the predictions, I can click save here and say save unstandardized predictions and click OK at that point. And that will actually show me a predicted value. I'm just going to get rid of the decimal places here to make it easier for you to see. And I'm even going to change it to dollars, so you can see that's actually dollars predicting here. And this is the dollars that's predicting against the actual value. We scroll down the bottom here. Notice this very last case here. It doesn't have salary, but it does have the model. So it's applied the model even though it doesn't have the variable salary, and it's predicted what this person's salary is based upon their beginning salary and the other factors in it. So this is one way in which we can get it to score data. We simply add extra rows onto the end where the target field is unknown. An alternative way to do this is to save the model. You can go and say save the model away as an XML file. So you can say I want to call this regression webinar. I'm going to call it that and say save that. And hit continue. It says you want me to replace it. It's already there. I say, yeah, run that. Click on run. And then if I open up a data set here, I've got employee unknown current salary. That means we've got the employees here, but we don't know what their current salary is. That's literally been deleted from the data set. We could then use that previous model that we've created to score the data. So we could go to the scoring wizard here and say, there's that regression webinar model I talked about earlier on. It matches up the fields. And I don't want the standard error. I just want the predicted value. I could say, I could change this to, predicted current salary to make it clear. Click next and hit finish. And there's the predicted current salary. Again, I'm going to get off the decimal places. And again, I'm going to change it to dollar. Click OK at that point. And there we have the predicted current salary using a model that we had exported as an XML file and using it to score the data set. So this is one way in which we can take a predictive model and use it to score a data set. Okay, that is linear regression. And that works as a good example in regression. What about logistic regression? Well, that's a very different approach and a very different way of working, a slightly different way of thinking, really. Let's just introduce that. Here, we're not trying to predict a continuous outcome. We're actually trying to predict a categorical outcome. Here's the category we're trying to predict, which is, do people have subscribed to a news channel? The idea being that this was some sort of cable news channel. I guess these days it would be like I don't know, a newspaper app subscription, something like that. Yeah. And we've got, 51% of people don't subscribe to it, 48.6% do subscribe to it. Can we predict using these demographic data and other data, the likelihood that somebody will subscribe to it using a regressive technique such as logistic regression? Well, to do that, a logistic regression is going to help because it allows us to predict things that linear regression can't, such as the response to a marketing campaign or people's credit risk in terms of, whether or not they're a good credit risk, or whether a subscriber is likely to renew a service, or risk of equipment failure, or how likely it is that a patient will be readmitted to hospital, or whether a charity donor will switch to direct debit. These outcomes are not continuous numbers, so standard linear regression won't work. And when the outcome consists of two categories, as it does here in this example, we use binary logistic regression. And when it has three or more categories, such as low, medium, high, or something like that, or three different product groups, we use multinomial logistic regression. And logistic regression gets around the limitations of describing relationships of straight lines by using a special sigmoid curve. And this is what the sigmoid curve looks like. So you can imagine here, we've got we're selling an iPhone or something like that, and we've got the iPhone at full price. Let's say that, there's just, if it's at full price, you're just not going to sell it. Why would somebody buy it from you rather than buy it directly from Apple if it's at full price? So the probability of responding to your offer is very small. But if we start to introduce a discount to it, then the probability of responding increases until suddenly we get this point where it kind of flips. There's a zone here, it flips. Until you've got 98%, discount at this point here, and probability of responding is very close to 1, right down to 100% discount where the probability is exactly 1. Well, the key here is what is these numbers here that's driving this? There's a special formula that converts the coefficients, the predictor coefficients on the x-axis when you're using logistic regression to these probabilities. And these numbers here are the coefficients that are produced within logistic regression. So I'm just going to show you what they look like. If I go here and I go to analyze, down to regression, down to binary logistic, two-category logistic, here's my variable here, accept news. I'm going to just pick up, say, education level in years. Let's pick that up first. We'll run that one first of all. So this is what the output looks like. Let me just hide the rest of the output here a wee bit so we can see this more clearly. Okay. So here's our output from logistic regression. It's basically giving us some measures here and what's called the case processing summary, telling us how many cases were passed through. 442, none missing. The dependent variable encoding here is basically it's saying, look, I don't know how you've coded the categories in the dependent variable, the target variable. They might be coded as, 1 and 2 or 2 and 3. But for my purposes, it codes 0 and no as 0 and 1 as yes. That helps work out. And then it says, okay, beginning block 0, that means without using any variables, this is what I would predict. And it says, I would predict everybody to be a no because there's slightly more no's than yeses. And I would be right 51% of the time. That's kind of your contrast. And that would be using just a constant, which relates to, just that average value there. Is that statistically better than taking a wild guess? Not really. So it's not non-statistical. Variables not in the equation at this moment is education levels in years. And then it says, okay, uh, as I add in these variables here, does it help in any way? Does it actually help me predict this outcome? Well, it's giving me various levels of fit at this moment, and they're very, very weak. Education level years isn't really strongly related to this. It's saying, look, if you were using that, you'd only be 52% accurate overall, which isn't much of an improvement. The omnibus test here is saying, look, that's non-significant. It's not much better than a wild guess, this particular variable here. And it's giving me these weird coefficients at the bottom here. Well, these weird coefficients, this B value here, doesn't mean you multiply education by 0.049 because, of course, we're talking about a probability outcome here, not a true number. It's actually saying we'd need to convert this. This is actually refers to what's called the log of the odds, which is really quite an obscure way to think of it, but it's part of the formula that these coefficients go through in order to create the predicted probability outcome. Let's swap it around. Let's try something else. Let's try age in years. Okay, let's see if that helps. Click OK. Try that time now. Okay. Now we've got these fit statistics. The -2 log likelihood is again very, very obscure number, but basically the smaller that value is, the better the fit. And here we have R squares that we saw beforehand in linear regression. These are what are called pseudo R squares, so kind of pretend R squares. And again, the higher these are, the better they are. I wouldn't really interpret them too closely in the same way that we would linear regression. This is kind of roughly 14%. And we can see here that if we're using this variable age in years, that we're 64% accurate. That is statistically significant, hence our omnibus test here saying, yes, this is better than a wild guess. And here we would put this age in years through this equation here of 0.054. And it gives us something called an exponentiated B value. That tells you how many times the probability is increased, or that the odds are increased of them buying the new service for every 1 unit increase in age. And it's saying you're 1.05 times, quite a small number, but remember there are many age values here, for every unit increase in age. Let's do another one. I'll do another one here. I'm just going to choose this. This time I'm going to use gender. Gender's categorical. So I'm actually going to go categorical here. And with a categorical variable here, what I can do is I can tell it which variable, which category I'm interested in. I'm interested in comparing males to females. Females is higher coding than males, so it's called the last category. The reference category is the last category. It's called the reference category. And if I put that in, it's actually giving me a value here where again, it's significant. It's saying you'd be 57% accurate. Gender is significant. Again, this obscure value here of 0.597 log odds. But here the exponential B value is quite interpretive for us. It's quite helpful. It's saying that you are 1.8 times more likely to buy this, or 1.8 times odds more likely to buy this. The odds are greater, 1.8 times odds greater that you will get this service if you are male compared to the reference category of female. So it's showing us the effect of, because there's only 2 values here, unlike age where there's a range of values, it's quite a brutal shift. So it's saying, this is the odds ratio. This is used a lot in medical interventions where you're saying, okay, if we give this sort of treatment, how does the odds of survival affected by it? We put all of the variables in. Let's pick them all up and chuck them all in. And again, I'm going to use forward here, forward conditional. Click OK. I'm going to get, you can see it actually adds in three variables, and we can see the R square value going up. We can see the -2 log likelihood going down, which means better fit. And we can see that by the third step, the third variable's been entered in there, we're 66% accurate. Here's our variables in the equation. Let's just once again, I can't put the steps in there, unfortunately. So I'll just look at step 3, variables in the equation. It added in gender, it added in education level in years, it added in age in years, and we have a constant value. And it's showing us exponentiated B values, which show us whether or not an increase in these numbers increases the odds that you're going to take up the subscription or not. And if we were to save this out as an equation and have it save predictions for us, it's actually going to save the probabilities for us. And it's saying, here's the probability that you are in the yes group, that you will buy it. I think you're a 67% chance you'll buy it. So therefore, I predict you to be a no. I think there's a 19% chance you'll buy this one. I predict you to be a no. I think there's a 75% chance you'll buy this. I predict you to be a yes. And you can see there's quite a lot of agreement here. Here's one where it disagrees. It says, I think this person has an 83% chance of buying this. Predicts them to be a yes, whereas in reality, it's a no. So that's a quick tour through logistic regression, how it's very different from linear regression, because you can't talk about a 1 unit increase in a variable having an effect on the outcome. Here we have to get it to say what increase does it have on the odds of you being in one group or the other, and the resultant equation produces not a numeric value such as predicted age or predicted salary. Instead, it produces a probability value, which we can interpret in percentage terms of the likelihood of you being in probably the key group, the target group here, yes. This is a very powerful method. It's a very robust method. It's used very extensively in statistics and machine learning. It holds up very well, actually, as a method compared to more modern machine learning techniques. People would often compare things like a neural network's performance against logistic regression, even though logistic regression is much older than neural network, but it's often the baseline against which other types of more sophisticated, if you like, or more modern predictive techniques are compared. So if you have the regression module in SPSS, you will get logistic regression plus a number of other types of regression. If you don't have the regression module, you'll always get at least linear regression. So with the regression module, you can go beyond linear regression to unlock many other types of regression functionality. What other things we want to point out here? Just the fact that there are some additional resources you might want to look out for here related to regression and linear regression, such as how to model nonlinear relationships, introduction to a technique called moderation analysis and mediation analysis. And there's also some links here to help you figure out what version, which modules you've got installed within SPSS yourself, and exactly what's included in the regression module, as well as stuff related to choosing the correct statistical tests, and some blogs here on statistical testing and various procedures. For people who are customers of Smart Vision, you have free access to our online training materials. Other non-customers can purchase these on an individual basis. Be aware that we do offer a range of consulting services in various bite-sized chunks, whether it be project support or more deeper analytical engagements. Might be 1 to 2 days or more, 1 to 2 weeks if necessary. And you can source your software directly from us. We can also help with training consultancy services, whether it be virtual training or in-person delivery, classroom training. We will offer no strings attached advice to anybody that pretty much reaches out to us. And for people who are customers of Smart Vision, we do offer also technical support services. So you don't have to go to IBM for your technical support. You can come directly to us. And people usually find that we're usually a bit quicker and a bit easier to deal with. In the meantime, I hope you find that useful, and we look forward to you logging in again in the near future. Thanks very much.